Good morning, students.
Good morning, ma'am.
Okay. So in the previous class, we discussed about the sharpness of resonance. And through some derivations, we proved that the sharpness of resonance is something that we can better explain with the help of quality factor. So you don't need to study all these entire derivations and proof. You just try to understand the concept. Sharpness of resonance can be explained with the help of quality factor. Then what do you mean by quality factor, Gauri?
It is defined as a ratio of the inductive reactance to resistance.
It is the ratio of inductive reactance to resistance, or one more definition.
It is a ratio of capacitive resistance to resistance.
Capacitive reactance to resistance. So it can be the ratio of inductive reactance to resistance or capacitive reactance to resistance. And this quality factor is something that is equivalent to that of the sharpness of resonance. Naurin, what is the equation for calculating the sharpness of resonance?
Omega 0 by 2 delta omega.
Omega 0 by 2 delta omega. It is the ratio of resonant frequency to that of the bandwidth, where 2 delta omega is the bandwidth difference in frequency between the upper half frequency and that of the lower half frequency, and omega 0 is the resonant frequency, that is the frequency at which the resonance condition is occurs. So at this resonant frequency, we know that the current reaches a maximum value. So that's all about the sharpness of resonance. You don't need to bother about the entire derivations and proof. It's a huge derivation. Through that steps, we are proved that the sharpness of resonance is something that is related to that of the quality factor. So today we are moving to the next topic, that is LC oscillations. All of you write the next heading, LC oscillations. LC oscillations. In order to explain this LC oscillations, can you guess what are the two components that we are going to consider here?
Inductor
And capacitor. So here we are not considering the resistance. In order to explain the LC oscillation, we are going to consider the L for inductor and C for capacitor. So first of all, we are going to find an equation for calculating the frequency of LC oscillation. After that, we can explain the working of or how we can construct and work the LC oscillator and all. So students, we can start this derivation by considering the resonance condition. So according to resonance condition, by resonance condition, so resonance condition,
chi L minus chi C is equal to 0.
chi L minus chi C is equal to 0, or we can say chi L is equal to chi C. Chi L is equal to chi C. Or we can write, instead of chi L, we can write L omega. L omega is equal to, what about chi C?
1 by C omega.
1 by C omega. So here we have started the derivation by considering the resonance condition. Under resonance condition, we know that chi L is equal to chi C, or L omega is equal to 1 by C omega. Now we are going to just rearrange the equation by taking this omega to LHS. So it becomes, so we have L omega is equal to 1 by C omega. Now we are going to take this omega to the LHS. It becomes L omega square is equal to 1 by C. Now we can take this LHS from, now we can take this inductance L from LHS to RHS. It becomes omega square is equal to 1 by LC, which implies omega is equal to 1 by root LC. So here we are starting from the resonance condition. Chi L is equal to chi C. Chi L means inductive reactance. Inductive reactance is given by the equation L omega. Chi C is given by 1 by C omega. Then the next two steps are just rearranging by taking the omega from RHS to LHS. And in the next step, we take this inductance L from LHS to RHS. So we get omega square is equal to 1 by LC. If omega square is equal to 1 by LC, we can say omega is equal to 1 by root LC. Yes? Is there any doubt regarding with the steps? Okay. Then we know the equation for angular frequency, relation between angular frequency and that of the linear frequency. What is the relation between angular frequency and linear frequency? Omega is equal to?
2 pi.
Very good. Omega is equal to 2 pi f. According to the relation between angular frequency and linear frequency, we have omega is equal to 2 pi f, where omega is the angular frequency, f is the linear frequency. So in the previous case, we have an equation for omega. Omega is equal to 1 by root LC. Then the relation between angular frequency and linear frequency, we have another equation for omega, that is omega is equal to 2 pi f. So here the LHS of these two equations are equal. So we can equate these two equations. So it becomes 2 pi f is equal to, equating the above two equations, we get 2 pi f is equal to 1 by root LC. 2 pi f is equal to 1 by root LC, which implies f is equal to 2 pi f is equal to 1 by root LC, which implies f is equal to
1 by 2 pi.
1 by 2 pi into root LC. So this is the expression for calculating the LC oscillations. So this is the expression for calculating the frequency of LC oscillation. The frequency of LC oscillation is given by f is equal to 1 by 2 pi root LC. Here we are not explaining what you mean by LC oscillation and all. Before that, we are just describing an equation for calculating the oscillation that is generated by an LC oscillator. So now we are going to explain what you mean by LC oscillator and how this LC oscillations or oscillations are generated by this LC oscillator, and how we can explain or how we are derived this equation of frequency of LC oscillation from that of the circuit and all. Okay, so you just kept this equation in your mind. The frequency of LC oscillation can be calculated by f is equal to 1 by 2 pi into root LC, where f is the frequency, L is the inductance, and C represents the capacitance. So now we can represent or we can discuss what you mean by LC oscillator. Okay, so first you just think in your mind, as the name implies, LC oscillations. So here we are consider only the two electrical components. One is inductor and other is capacitor. Here we are not considering the resistor. So LC oscillation, as its name implies, here we consider inductor and capacitor. We are considering the inductor and capacitor. Consider a circuit which contains a capacitor. It is connected to an inductor. Inductor is something that is in a coil form. Capacitor is represented by a parallel plate. So here we consider, in order to explain this LC oscillation, here we consider a capacitor which is connected to an inductor. Okay. Now, initially the inductor and capacitor is not charged. They are uncharged state. Then with the help of a battery, we are charging this capacitor. Okay. So at the beginning state or at the initial state, the inductor and the capacitor doesn't contain any amount of charge. They are in uncharged state. But with the help of a battery, we are charging this capacitor. We are charged this capacitor. Then one plate of the capacitor becomes positively charged and the other plate becomes negatively charged. With the help of a battery, we charging the plates of capacitor such that one plate is become positive charged and the other plate becomes negatively charged. Then the charge stored by the capacitor can be taken as UC is equal to half CV square. With the help of a battery, we charge the capacitor such that one plate of the capacitor becomes positive charge, the other plate is negative charge. So we can write the charge stored inside the capacitor is given by UC is equal to half CV square. But at the same time, the inductor remains uncharged because the charge is only provided to the capacitor. That during first case in the initial case, the charge stored in the inductor is equal to 0. Now, whenever the capacitor attains a maximum charge, we replace the battery. Okay, after attaining the maximum charge by the capacitor, we replace the battery. Then what happens? The capacitor starts to discharge. So initially there is no charge contained in the capacitor and inductor, but with the help of a battery, we have started to charging this capacitor. As a result, one plate becomes positive charge and other plate becomes negative charge and it attains a maximum charge. It is given by UC is equal to half CV square. But at the same time, inductor doesn't contain any amount of charge. So the charge possessed by the inductor is taken as 0. UL is equal to 0. Then the capacitor attains a maximum charge. We replace the battery. Then the capacitor starts to discharge. As a result, the positive charge from the capacitor is started to move from capacitor to inductor. Okay, so in the second stage, what happens? Whenever we replace the battery, the capacitor starts to discharge. As a result, the positive charges are moves to inductor. That is, it starts to flow to inductor. So in the second stage, what happens? All the charges from this inductor is moving from positive plate to the inductor. Yes.
Can you tell the point again where VL is equal to 0?
In the initial state, that is in the very beginning of this experiment, or in the case of LC oscillator, they are in uncharged state. Then with the help of a battery, we are charging this capacitor. So with the help of the battery, one plate of the capacitor becomes positively charged and the other plate of the capacitor becomes negatively charged and it attains a maximum charge. Then the charge stored by the capacitor is given by UC is equal to half CV square. In the same time, inductor doesn't contain any amount of charge. It remains uncharged. So we can write the charge stored in the inductor in the initial case is equal to 0.
Okay.
Then whenever this capacitor is attains a maximum charge, we replace the battery that is in connection with the capacitor. After attaining the maximum charge by the capacitor, we replace the battery. Then what happens? Automatically, the capacitor is started to discharge. As a result, the positive charge from the capacitor is started to move from capacitor to inductor. That is what we are going to discuss in the next case. So in the second case, the charge from the capacitor is started to move from this positive side to this inductor in this direction. The charge flow is occurs. And then what happens whenever the charge is enters into this inductor? Inductor is nothing, it is in the form of a coil. What happens? The magnetic flux associated with the coil is changes and it becomes charged, or the current is started to flow through this inductor, or it is attains a maximum energy. In the second case, the charge from the capacitor is moves to inductor. Whenever the capacitor is discharges, the positive charge from this capacitor is started to move through this inductor. When a charge is enters into this inductor coil, magnetic flux associated with the coil is changes. Thereby, it attains a maximum charge or maximum energy. So in the second case, the energy possessed by the inductor or the energy stored by the inductor is given by UL is equal to half L I square. Half L I square. But at the same time, what about the charge possessed by the capacitor? Try to guess. UC is equal to the 0, because the complete charge from the capacitor is moving from capacitor to inductor. Now this side becomes maximum charge. It attains a maximum charge, and the maximum charge attained by this inductor is given by UL is equal to half Li square. At the same time, the capacitor is fully discharged. That is, it contains no charges. UC is equal to 0. Is it clear?
Yes, ma'am.
Okay.
Now,
Again, yes.
but the other point, can you explain, like change in magnetic flux?
Okay. Whenever the charge is reaches into the inductor, the magnetic flux associated with the inductor is changes. That is what is we were discussed in the chapter electromagnetic induction. So a charge is moving towards the coil. As a result, the magnetic flux associated with this inductor coil is changes. It attains a maximum charge. Thereby, it attains a maximum charge because a voltage is induced here and an induced EMF is developed. It attains a maximum energy or maximum charge. That maximum charge stored by the inductor is given by UL is equal to half Li square. Again, as in the case of capacitor, here when the inductor attains a maximum charge, it started to collapse. Just like that of the capacitor, here also, whenever the inductor is reaches a maximum energy level, the inductor is started to collapse. Okay, so in the second stage, actually the charge from this capacitor is reaches in this inductor. Then the magnetic flux associated with this inductor is changes. It attains a maximum energy. The maximum energy stored by the inductor is given by UL is equal to half Li square. At this stage, the capacitor becomes 0. Energy stored in the capacitor is 0. Then in the third case, what is actually happens? Whenever this inductor is attains a maximum energy level, it is started to collapse. So then the energy from this inductor is started to move into this again into capacitor. So in the third case, capacitor is started to collapse. Sorry, not capacitor, inductor. Inductor is started to collapse. So the energy from this inductor is reaches here in the capacitor plate. As a result, this downward plate is becomes positive charge and the upper plate is becomes negative charge. Because here the charge is enters in this direction, thereby making this lower part of the plate, capacitor plate, becomes positive and the upper plate becomes negative, just opposite to that of the initial case.
Can you say it once more, ma'am?
Okay. So in the third case, after attaining the maximum charge, inductor is started to collapse. After attaining the maximum charge, inductor is collapsed. Charge from this inductor is now moves towards this capacitor. Charge from this inductor is moved towards, or it is reaches to the capacitor. So the plate which is initially negative becomes positive. So the plate which is initially negative becomes positive. And the plate which is initially positive becomes negative. And the plate which is initially negative becomes positive. And the plate which is initially positive becomes negative. Again, what about the energy stored in the inductor in this case? UL. Yeah, it's right. Unmute and say.
0.
It's zero because the maximum energy, after attaining the maximum energy, it started to collapse. So all the energy from this inductor is now reaches into the capacitor. So in this stage, the charge possessed by the inductor is equal to 0. Then what about the charge possessed by the capacitor? Charge possessed by the capacitor becomes equal to
Half CV.
half CV square. So in the third case, after attaining the maximum charge, inductor is collapsed. Inductor started to collapse. Then the charge stored by the inductor becomes equal to 0. The charge from this inductor reaches into the capacitor, thereby making this plates of the capacitor positive and negative respectively. That is, it makes the plate which is initially negative becomes positive and initially positive becomes negative. And the charge stored in the capacitor is given by UC is equal to half CV square. Charge or the energy stored in the capacitor is given by UC is equal to half CV square. Here once again the same phenomenon is occurs. What happens? Capacitor is attains a maximum charge. Whenever it attains a maximum charge, what happens to capacitor? It discharges again. Okay. After attaining the maximum charge, the capacitor is again started to discharge. Okay. Then the charge flow is occurs in the backward direction, that is from positive to inductor, that is just opposite to that of the initial case. So in the fourth case, here we have the inductor, this is the capacitor. Now here the plate is positive, here we have negative. So in the fourth case, after attaining the maximum charge, capacitor started to discharge. Then charge from the capacitor is reaches into the inductor in a backward direction, that is from positive to negative, just opposite to that of the initial case. So in the fourth case, the charge stored in the capacitor becomes equal to 0 because all the charge from this capacitor is reaches from capacitor to inductor. It is reaches or it is moves from capacitor to inductor. So in this case, the charge stored in the capacitor is become equal to 0. UC is equal to 0. At the same time, the same amount of the charge or the energy is obtained by this inductor. Then the charge or the energy stored in the inductor becomes half Li square. So this process is continuous. So this is what is known as LC oscillation. That is the back and forth oscillation of charges or the energy between inductor and capacitor is known as LC oscillation. This process is continuous and continuous. Again and again it continues the same process. So the oscillation of charges or energy, the oscillation of charges or energy between this inductor and capacitor is known as LC oscillations.
So slowly.
Okay. The oscillation of energy, the oscillation of energy or charges, the oscillation of energy or charges between this inductor and capacitor. Before that oscillation, the back and forth oscillation, because in the first case, the charge is oscillated in the upward direction. In the last case, we are discussing the charges are oscillated in the opposite direction. So the back and forth oscillation, of energy and charges between the inductor and the capacitor are known as LC oscillations. Or you can copy down this slide. Whenever the energy is given to a circuit, that is with the help of a battery, we are giving energy to that of the capacitor containing a pure inductor of inductance L and capacitor of capacitance C. The energy oscillates back and forth between the magnetic field of the inductor and the electric field of the capacitor. Thus, the electrical oscillation of definite frequencies are generated. These oscillations are called LC oscillation. So this explains the entire phenomenon that is takes place inside the LC oscillator. Or in simpler words, you can say it is the back and forth oscillation of energy and charges between the inductor and capacitor. This oscillation is known as LC oscillations. Whenever energy is given to a circuit containing a pure inductor of inductance L and a capacitor of capacitance C, the energy oscillates back and forth between the magnetic field of the inductor and the electric field of the capacitor. Thus, the electrical oscillations of definite frequencies are generated. These oscillations are called LC oscillations. Is it over? Can I change the slide?
Yes.
Okay. Now write the next heading. We are going to derive an expression for frequency of oscillation from this LC oscillator. Okay. Frequency of oscillation. The same equation we obtained, that is F is equal to 1 by 2 pi into root of LC. So with the help of applying the Kirchhoff laws, we are going to derive an expression for frequency of oscillation. So all of you write the next heading. Frequency of oscillation. Frequency of oscillation. By applying the Kirchhoff laws, we know that according to Kirchhoff loop rule, the second rule, the product of current and that of the resistance of a closed loop will be equal to that of the EMF of the circuit. Okay. So applying the Kirchhoff laws, we can write VC plus VL is equal to 0. So here VC and VL indicates the EMF that is generated in the capacitor and that of the inductor. Instead of the EMF E or epsilon, here we are using the term V itself. So by Kirchhoff laws, we can say VC plus VL is equal to 0. It is in the form of a closed loop. The inductor and the capacitor is connected in a closed circuit. So we can say the sum of their EMF is equal to 0. What about the EMF or the voltage corresponding to capacitor? EMF or the voltage corresponding to capacitor. We know that the charge stored in a capacitor is given by Q is equal to CV, which implies V is equal to
Q by C.
Q by C. So here we can write Q by C plus, what about the charge stored in an inductor? EMF induced in an inductor. We already discussed an expression in our previous lesson, electromagnetic induction. EMF induced in an inductor is given by epsilon is equal to minus of L di by dt. Did you remember this equation? In self-induction, we are deriving an expression for EMF. Induced EMF is equal to minus L di divided by dt. But here we don't need to consider this negative sign because it indicates the direction and all. We just consider here instead of E, we are consider V. VL is equal to L into di by dt. So it becomes Q by C plus L di by dt is equal to 0. Where VC is equal to Q by C and VL, EMF generated in the inductor is given by L into di by dt. So Q by C plus L di by dt is equal to 0. Or we can write L di by dt is equal to minus Q by C. So Q by C plus L di by dt is equal to 0. Here we take this Q by C to RHS. So it becomes L di by dt equal to minus Q by C. Or di by dt is equal to minus Q by LC. Here we take this L from LHS to RHS. So it becomes division in the denominator. That is, it becomes minus Q by LC. di by dt is equal to minus Q by LC. Again, what do you mean by current? Here we have di by dt, rate of change of current, where I is the current, Q is the charge, L is the inductor, and C is the capacitance. Then what do you mean by current?
Rate of change of charge.
It is the rate of flow of charge. Or we can write I is equal to dq by dt. I is equal to dq by dt because current is nothing. It is the rate of flow of charge d by dt of q. So instead of this I, here we can substitute this dq by dt. So our equation is this di by dt. Di by dt is equal to minus q by LC. But we know that I is nothing. It is the rate of flow of charge dq divided by dt. Therefore, we can write d by dt of I. I is dq by dt. d by dt of dq by dt is equal to minus q by LC. D by dt of dq by dt means d square q divided by dt square. D square q divided by dt square is equal to minus q by LC. D square q by dt square is equal to minus q by LC. Or we can write d square q divided by dt square plus q by LC is equal to 0. D square q by dt square plus q by LC is equal to 0. Now we are going to compare this equation with that of the equation that we are already studied in +1 physics of oscillations. Did you remember the equations corresponding to oscillations that we are already studied in the previous year? In +1, the equation for oscillation is given by d square x divided by dt square plus omega square x is equal to 0. So this is the expression for oscillations. According to the equation for oscillation, we have d square x by dt square plus omega square x is equal to 0. So here we are going to compare these two equations. This equation is also, we get a differential form of oscillation, and this is the general equation for calculating the oscillation. Here we are going to compare these two equations. So here we have, instead of charge q, we have the term x. Instead of charge q, we have x. Similarly, here we have, instead of omega square, which term you can find in this above equation instead of omega square?
1 by C.
Yes. Instead of omega square, we have 1 by LC. Okay. So by comparing these two equations, we can write, omega square is equal to 1 by LC. We only need this term in order to explain the frequency, because here we are going to deriving the frequency of oscillation. So by comparing the above two equations, we get omega square is equal to 1 by LC, or omega is equal to 1 by root LC. Omega square is equal to 1 by LC, or omega is equal to 1 by root LC. Again, as we told earlier, there is a relation between angular frequency and that of the linear frequency. It is given by omega is equal to 2 pi f. So we can equate these two equations. So we get 2 pi f is equal to 1 by root of LC. Which implies f is equal to 1 by 2 pi into root of LC. Therefore, frequency of oscillation is given by F is equal to 1 by 2 pi into root of LC. You can go through any of these two derivations, but you must study the final expression for calculating the frequency of LC oscillation. That is F is equal to 1 by 2 pi into root of LC, where F is the frequency, L is the inductance of the inductor, C is the capacitance of the capacitor. And here we just prove that this is the equation we are deriving for calculating the frequency of LC oscillation from that of the LC oscillator. Is it clear?
Yes, ma'am.
Okay. So here we have one more topic left. In real case, we cannot say this LC oscillation or LC oscillator is work possible. So here you can write one question. Why LC oscillations are not realistic? Why LC oscillations are not realistic? So in real case, actually this LC oscillation, sometimes it is not practically possible. Because in this explanation of LC oscillation, we are explained that it is actually a continuous process. That is, the back and forth oscillation takes place between this inductor and capacitor, and it is continuous. Takes place continuous. But in the real case, it is practically not possible because every inductor has some resistance. Every inductor possesses some kind of resistance. So the effect of this resistance is to introduce a damping effect on the charge and current in the circuit, and this oscillation finally dies away because the inductor must possess a kind of resistance. This resistance causes some kind of damping effect on the circuit. As a result, the oscillation is finally dies away. It is not continuous. As a result of the resistance possessed by this inductor, finally we can say that the oscillations possessed by this LC oscillator is dies. It is not continuous. And the second reason, even if the resistance were zero, even though if we are just imagine if the resistance possessed by the inductor is equal to zero, the total energy of the system would not be remains constant. The total energy of the system is not remains as a constant. It is radiated away in the form of electromagnetic waves. It is radiated in the form of electromagnetic waves. So that electromagnetic waves that we are used for the working of radio and the television. So practically, this LC oscillations are not possible. We can explain the continuous back and forth oscillation takes place between the inductor and the capacitor and all. But in real case, actually, we can say there is some kind of resistance possessed by this inductor. So as a result of this, it causes some kind of damping effect on the circuit. Then the oscillation is finally dies away. It is not a continuous process. The second one, even though if we are consider the resistance offered by the inductor is equal to zero, the total energy, some kind of the energy of this oscillation is dissipated away in the form of electromagnetic waves. That is, the total energy of the system is not remains as a constant, just like UL is equal to 0 and UC is equal to half CV square. We cannot say it's a constant value. It can be changed. It may be changed.